Okay, let's get started. Let me share my screen. Okay, could you see my screen, everybody?
Yes, I
Can
can
you?
see it.
Yeah,
Yeah,
yeah. You see the midterm exam 2 information, as I already mentioned in last class. You will take the midterm exam 2 on October 21st. This means coming Wednesday. And then here I have mentioned the usual time, I mean class time, 9:10 to 10:05. But again, like I will extend likewise the last time, probably from 8 a.m. to until noon, 4 hours duration. You have to answer and then you have to upload. Therefore, total 4 hours is including writing the answers plus scanning and uploading on the Dropbox. So again, I will remind you on Monday. And in terms of syllabus, you will be looking class 15 through 26. 26, it will be on Monday. Today actually it will be 25. So Monday it will be 26. So therefore the thing that we will be covering until Monday, that is the syllabus. And you will start looking 15. Therefore, in terms of chapter application of Laplace to circuit problems, and then frequency response, and currently we are dealing with magnetically coupled circuits. And then if you see the book that we are looking, chapter 13, 14, and 15. 14 was Laplace, 15 was frequency response, and then on the backward, 13 is that magnetically coupled circuits. So therefore 13, 14, 15. And then again, likewise, the last time, you will be asked 4 or 5 questions, numerical problems mainly. So does anybody have any questions? So and then on Monday, I will discuss with you the solution for homework set 4. And hopefully within Saturday or Sunday, your grading will be ready for homework set 4, and then I will notify you. And then on Monday, I will discuss with you the solution for homework set 4. And then you all are ready. Therefore, I would recommend you all, please, you make lots of practice and practice. Circuit problem, that's the only thing. Even though you understand, so you have to make practice to get the correct result. Yeah, then you are fine. Okay, so moving forward, everybody see, last class, we were discussing the transformer. And then we were discussing this slide. And then at the end, Julian asked question about that wireless charging. And then we ended the class. Uh, so as you can see once again, today we will be solving few numerical problems. So at that time, these equations will be helpful for you. So you see that from this circuit, magnetically circuit for ideal transformer, we derived this on secondary voltage, which is proportionate to d phi by dt. And then Ns is the proportionality constant, where Ns stands for number of turns on the secondary. Then similarly, Vp, this is the primary side voltage. It is Np d phi by dt. And then look this equation. Let me do a little bit bigger. This equation, for example, this is equation number 1, this is equation number 2. Then if you divide this equation by this equation, you will be getting this one. You see, Vs over Vp, d phi by dt, d phi by dt cancelled. So Ns over Np. Now that Vs is the secondary side voltage, Vp is the primary side voltage. And again, similarly, Ns is the secondary side number of turns and Np is the primary side number of turns. And that Np over Ns, sorry, Ns over Np, that term is called turns ratio. Turns ratio. This means what is the relationship between number of turns, primary, secondary, and then primary. That is the meaning of Ns over Np. And that is the primary functional characteristics of any transformer. If you remember, in the last class I was telling that just by controlling the number of turns, you can control the magnitude of the current. For example, if you apply 100 volt here, if you like, you can get 1000 or like point on million, whatever voltage you might get it just by controlling the number of turns. So that's why that is the relationship. Similarly, you can control the current as well. Now, from today, everybody, you will remember this equation. Always you will need this equation. Once transformer come, this equation will be related to it. And I mean, you can do the other way also. Like in this case, I'm dividing this by this one, but you can divide this one by this one. So the same thing. So therefore, in that case, Vp will go numerator, Vs will come denominator, Np will go numerator, Ns will come denominator. The same thing. So either way you can remember, either as it is, Vs over Vp, Ns over Np. Sometimes you will notice in some book or some literature or any article magazine, then instead of S and P, symbol 2 and 1 is used. So this means this is number 1 side, this is 2 side. So therefore by the symbol, for example, if I say here instead of VP, V1, then you will assume that that is the primary side, where first you will apply the voltage. If you see the symbol 2, you will assume that is the secondary side. So meaning is the same, exactly. Similarly, here you can see N2 over N1. The instead of primary, secondary, even you might say symbol 1, 2, etc. Then accordingly, this one also. Okay, so now if you see, as I was telling that NP over NP, that is called the turn ratio. So it might be like NP over NS as well. So both it is the same. Sometimes it is NS over NP, sometimes it is NP over NS. So it is the same meaning, keep in mind. Now, everybody say, don't you think that as I am saying, that if I apply 100 volt here, and then you might get 1000 volt or 100,000 volt, or you might get 1 volt or whatever, you can increase or decrease. So therefore, doesn't the question that how the voltage is increased? Because you know that law of conservation of energy, if you think from the viewpoint of the energy of this side and this side, energy should be the same, right? Yeah. The law of conservation energy is neither created nor destroyed. It is just converted from one form to another form, right? So from the physics, you all know law of conservation of energy. So now I'm saying that, okay, this equation is telling if you apply 1000 volt, you can make 100 volt or you can increase. So then how is that possible? So with the increase and decrease, it is not changing the energy on both sides. No, that definitely energy is being maintained the same. Everything follows that law of conservation of energy. So this means that when you are increasing the voltage in this side, meaning that current is decreasing. So the multiplication of voltage and current is the same on both sides. For example, you see in this side, primary voltage is VP, primary current is IP. So the multiplication of VP IP, that is the power in this side. Similarly, in this side, multiplication of VSIs, assuming that the load is connected, that is the power on the right side, secondary side. Therefore, both side power should be the same, right? So VPIP, that should be equal to VSIS. Otherwise, law of conservation of energy will not be maintained. So that is the reason that once voltage increase here, current decrease. Or in this side, if voltage decrease, then current will increase. In that way, they are maintaining the balance on both sides. So therefore, what thing I am explaining, so everybody see this one. So again, I am showing that equivalent circuit. So this is the equivalent circuit of transformer, ideal transformer. Then once again, this is primary voltage source. On the secondary side, the load is connected. So voltage is Vs. EP is the induced voltage. ES is the secondary induced voltage. Primary current, secondary current. NP, NS primary turns, secondary turns. And then see this relationship, what is written, VP over VS. That thing we looked here in the previous slide, this one, VS over VP, but next time I am writing VP over VS, NP over NS. But then you see the current thing is opposite. Current is not IV over IS. So everybody see this thing, relationship of three things. VP over VS is NP over NS. It is easy to remember. Like P here, S here, S here. But you look the current is opposite. IP is here, but IS is here. So, and why that is happening? You read, so everybody look this one. Incoming power, which is VPIP, equals to outgoing power or secondary power, VSIS. And why I wrote that on? Everybody read this thing, exactly I told, that ideally the transformer is perfectly efficient. All the incoming energy is transferred from the primary circuit to the magnetic field and into the secondary circuit. Therefore, this magnetic circuit is the via, this is the media. Primary energy is going into magnetic field, that magnetic field is transferring power on the secondary. Then in both way, the energy is the same. Therefore, if this condition is met, then the incoming electric power must equal the outgoing power. That's why I am writing. This is that law of conservation of energy. And then now if you see this equation, look this equation. So you can make relationship. So Vs over Vp, then you are getting Ip over Is. But what is Vs over Vp? That is the thing we looked last time. That is Ns over Np. That's why it is written Ns over Np. So therefore it is written here in that way, but here it is written as I said, you can write instead of Vp here, then Vs here. Either way, it is the same thing, same meaning. So therefore, from today, everybody you will remember whatever this form or this form, this is the transformer relationship between primary current, secondary current, primary voltage, secondary voltage, and then primary number of turns, secondary number of turns. This is the relationship. So this relationship will help you to solve, most of the problems. Uh, Everybody, do you understand me so far?
Yeah.
Yes. Yes. So therefore, everybody, please in your note draw this circuit. Soon I will show you a numerical problem. Everybody, please draw this circuit. Keep it handy and then write down this equation. This equation or this equation, as I said you, it is the same. Exactly, meaning is the same. So everybody, please draw this circuit, equivalent circuit of transformer, and then this relationship. And then I am going to the next slide. That will help you to solve the problem. So on the right side, this symbol indicates this is the load. Load will be connected on the secondary side. Therefore, it is showing that okay, some load is connected. In fact, in real practice, customers like we are connected at this end of the transformer, secondary side. So have you all seen this transformer device somewhere in Memphis City, nearby your home or somewhere? Have you noticed the transformer?
Yes.
Yeah, there are many. In fact, like we are connected to MLGW, right? MLGW is our power provider. Therefore, first MLGW purchases power from TVA, Tennessee Valley Authority, and they take power at 115 kV. So in this site, 115 kV. Then MLGW reduces to 25 kV. So therefore, at MLGW, their first voltage that is starts 25,000 volt or 25 kV. After that, there are lots of this type of transformer, all like step down. That changes to 11 kV, from 11 kV to 208, and then finally we get power at your home that is 120 volt. So that's why if we assume that this is the MLGW service station center, they are converting 115 kV to 25 kV. After that, there are many transformer in greater Memphis. Yeah, therefore, and then if any of the transformer get disconnected, then the connected customers goes under dark unless that is rectified, corrected. Okay, so I think I am assuming everybody have drawn and written down this equation, and then now look on numerical problem. Uh, Everybody read the statement. An ideal transformer is rated at 2400 slash 120 volt, comma 9.6 kVA, comma, and has 50 turns on the secondary side. Then calculate the turns ratio with the number of turns on the primary side and say the current ratings for the primary and secondary windings. So everybody see the very first line, the transformer is always transformer ratings, transformer specifications are always expressed in that way. So like 2400 slash 120, meaning that the 2400 is the primary voltage, 120 is the secondary voltage. Therefore, accordingly, it is called the step down transformer. I mean, transformer has various names. We will not go that detail. We don't need it in this class, but just keep in mind, it is called the step down type of transformer, meaning that it has the primary voltage 2400 and it is dropping down 20 times, going down, then it is 120. And then if you see the opposite thing, 120 is written here and 2400 written is here, meaning that 120 is then primary voltage, 2400 is the secondary voltage. In that case, you would call that step up transformer, because from low voltage you are going the upward, you are increasing the voltage. Accordingly, the transformer name goes step up. Therefore, when I say that we are connected to MLGW system, therefore sorry, you might see a transformer very close to your home or your neighborhood. That transformer definitely a step down transformer, because at your home you want to get 120 volt. Therefore, the neighboring transformer, which is the closest transformer with respect to your room, definitely that is a step down. That is not the step up. Do you understand what I am saying? So, therefore, for example, nearby your home, you will get this type of transformer, which are always step down, so that customers, people can use. Anyway, and then this thing, 9.6 kVA, this is the rating, power rating of the transformer, 9.6 kV. Now, can you see? Here the two things are written, 2400 slash 120, 2400 for primary, this is for secondary. And then here it is only one. This means 9.6 kVA, that is for both. It is the same for both. Left side is also that 950, right side is also the same. Because we learned this thing, everybody see, incoming power equals to outgoing power. That's why transformer power rating is only one. So that is the same for this side, same for that side. That's why in the statement, it just said 9.6 kVA. So you have to assume that that is for both. And then it says has 50 turns on the secondary side. transformer right side, this side has the 50 turns. Then the question is, first calculate the turn ratio. What is the number of turns primary side? 50 is on the secondary. What should be the turn number on the primary? As well as what is the current ratings for primary secondary? Now, this 2400 is the VP primary, 120 is the VS secondary, but the current values are not given. That's why it is asking what are the current ratings for the primary and secondary windings. Now here you see everybody turn ratio. First I am calculating the turn ratio. Turn ratio, just one thing keep in mind, turn ratio always denoted by the small letter A, turn ratio. It is basically the V2 over V1 or V1 over V2, or the, as you looked here, NP over NS, that is the turn ratio, which is denoted by symbol A. So just to keep in mind. So in this case, I am writing V2 over V1. So what is my V2? 120. And then 2400. So therefore I got 0.05. Now if you can do the other thing as well, still the answer is the same, correct result. Turn ratio is V1 over V2. If you do V1 over V2, then you will be getting 20. So therefore that is the same thing. Yeah. So either way you can do. So, and then accordingly your all calculation will go, then your result will be the same, whatever way you calculate. Okay, the next question is that, what is the number of turns on the primary side? Secondary side is given 50. So everybody look what I am writing. This time I am writing A equal to N2 over N1. Here I wrote a V2 over V1 because those two values were available. At the beginning, I don't have the primary number of turns. If I had the primary number of turns, then I could use the number of turns. I could use this equation. But here I am using this equation because that is available. And next time, because I got the value of this one, so next time I am writing N2 over N1. And then what is my N2? Secondary side, that is the 50. Everybody keep in mind, two symbol goes for the secondary, one refers to the primary side. So therefore, into 50, I need N1. So from here I am writing, so N1 is 50 over A. What is my A? This is my A. So I got 1000. I got N1 value 1000. This means primary side has 1000, but secondary side has 50. 20 times large. Accordingly, you see the voltage is 20 times smaller than the primary side because of this turn ratio or the turn number. And then question number C, current ratings for the primary and secondary winding. This means what is I1, what is I2. Everybody see what I am writing? This is the kVA. So kVA is the apparent power for the transformer. It is not kilowatt. So this is not the real or active power. This is apparent power. So that's why is V1 ion equal to V2 I2. This means I am following this one. This one. So I wrote that one. And why I wrote that one? Because I can see ion and I2. I have to find out the current for primary, secondary. So you see, here I cannot see ion I2. Here I cannot see ion I2. That's why I have to use this one. Now I can utilize this number, 9.6 kVA, which is the apparent power rating. So see, I'm writing this one. And then V1, my V1 is 2400, and then this is ion. From here I got ion is this number, 4 ampere. And then again, if I use this side, like S equal to V2 I2, then I will be getting I2 80. Therefore, see the current difference. Current is also 20 times. Therefore, pretty interesting thing, everybody look. Primary side voltage is 2400, but primary current is 4 ampere. Secondary side current is 120 volt, but then secondary current is 80 ampere. You see, pretty interesting. when voltage decreased, but then current increased. Here like voltage increased, but then current decreased. And in that way, they are maintaining the balance. I mean, this thing, law of conservation of energy. Therefore, energy is not getting lost, just it is getting transferred. So that's why when voltage increase, current decrease, current increase, voltage decrease. In that way, they are maintaining the balance and it is working. So everybody, could you follow this one?
Yes.
Could you solve B without determining the turns ratio, just going straight from the VP over VS equals NP over NS?
You can go, but here you see in the problem, you have only the secondary side number of turns. The primary turns is not given at the beginning.
Yeah, but you have both VP and VS.
Yeah, yes, and then you can write that equation. Of course, you can make that relation. You can say that V2 over V1, N2 over N1. That's right, yeah. You can do that. Directly you can go. So here, why I did in that way, because I went according to the question. First it said the find the turn ratio. You see, you look, Julian, you look. First it said turn ratio. So that's why I first, okay, those two voltage are available. First I did that. So therefore, what you are saying, you can do that, like V2 over V1 or V1 over V2 equal to N1 over N2. Then one side number of turns is given. Of course, you will be getting this one. So of course, what you are telling, that is right. You can do. And then once you get that one, then you can next time find out the turn ratio. But I started according to the the question being asked. Yeah, I just followed this thing. But what you are saying, that is also right. Is this fine, Julian?
Yes, sir.
Yeah. So everybody, do you understand this thing?
Yes.
Yeah. I mean, just look and think, and it's pretty interesting, and it's a not difficult thing. I mean, this is how the transformer works. I mean, we are getting the power with the help of the transformer. As I said in last class, I always treat transformer is like our heart of the body. So transformer is the heart of the power network. Without that, we cannot survive. I mean, we will not get power. Yeah. Okay. Now, there is one thing, another type of transformer. It is called auto transformer. Just I'll be talking for a minute, and then we will jump another numerical problem. So auto transformer, so you see what I have written, it has a single winding, part of which is common to both the primary and secondary simultaneously. So look the picture, this is on coil. Everybody look, this is on coil. And I am saying that, okay, the whole thing is the primary winding. For example, it has 100 number of turns. So therefore whole winding is the primary winding. And on that winding, I am applying the voltage, whatever it is. And then look, from this point, I am making a tapping. And then I am saying that this portion is the secondary. Therefore, for example, if you can assume that this is 100, number of turns 100, and then this one, for example, 50, 30, or 40, whatever. So, or you can increase. And if you fully take, instead of making tapping here, then like both primary and secondary side is the same. So therefore, because it is sharing the same winding, portion is primary and some portion is secondary, accordingly it is called the auto transformer. Now see this picture, it might happen that, okay, this is the full winding is on the secondary side where the load is connected, but in the primary winding, I am using a small voltage. So this means in this case, because this side is smaller than this side, okay, easily you can guess here there is like full number of turns, here some portion, 30%, 40%, 50%. It is called step up auto transformer because in this case, voltage will increase secondary. In this case, it is called step down because in this side higher voltage, this side will be lower voltage. It is called step down. Now, what is the application of this auto transformer? I mean, from real power network viewpoint, it is extensively used to interconnect to high voltage transmission lines operating at different voltage. Now, for example, as I was telling you that MLGW takes power from TVA, this side on 15 kVA, sorry, on 15 kV. This means 115,000 volt, and then it steps down to 25 kV. So in those cases, and then two are separate circuit. MLGW purchase power from the TVA. They pay money to TVA, and then they power us customers. We pay bill at the end of the month to MLGW. So therefore, this side is the load. This we are customers. We are the load. So we are connected to MLGW here, not here. So therefore, that is the thing. It is extensively used to interconnect to high voltage transmission lines operating at different voltages. Or it might be not MLGW. Again, for example, it will go to another network, let's say Mississippi, Arkansas, or other state. And then TVA sells power to 7 or 8 states of United States. So therefore, this side may have one voltage, this is other voltage. So this is the application. Therefore, at your level, like this thing, transmission line, those are like out of the syllabus of this course, we will not go. But I will give you one real example of this auto transformer. I mean, everybody, you have the ceiling fan, right? So have you ever seen that you can control the speed of the ceiling fan from a regulator? That regulator is mounted or placed on the wall. Have you seen this thing, that type of ceiling fan?
Yes.
Yes. So therefore, in most cases, what happens, like you have the ceiling fan and you have some sort of string connected it, and you can change the speed of the fan. But sometimes, like you said, yes, sometimes there is a regulator, fan regulator, that is mounted on the wall of the room, and from there is connection to the ceiling fan. And if you control a knob, then it will change the speed, meaning that actually you make this thing. Let's say everybody look this on left side figure. For example, your load is the ceiling fan load. Here it is ceiling fan connected, and ceiling fan is taking some portion of the voltage. Then definitely, if this side is 400, then this side is 100, 200, just an example. And ceiling fan is running. And then if you control this point, ceiling fan regulator mounted on the wall, okay, instead of here, you connect it here. This means now your ceiling fan is taking more voltage, it will spin faster. Its speed will increase. Or you say, no, I will decrease much more. I want to reduce the fan speed. So accordingly, if you make the tapping here, that is the regulator. It basically functions this on its function, either connection here or here or here or here. So that fan regulator is one of the best example of auto transformer. In also, have you seen this thing? Just a moment, everybody. One device is called Variac. So have you seen this thing in the lab, in any lab? I think we don't have anything in the circuit lab. So have you ever seen in any other lab this device Variac?
No.
Probably no, yeah. So therefore Variac means it is called variable AC, meaning that variable alternating current. So therefore this is a device. I think once you will go energy conversion lab, I mean 4201 code course, if you go, those who are electrical background definitely will go, you can see this device. So therefore typically it looks like that. It looks like circular, and then it is marked like 0 volt here, and then for example 10 volt here. In that way it is increasing, say it is 50 volt. in that way it is marked. You can go, I think, up to 230 volt. This means if you go clockwise, then gradually voltage will increase. And there are those type of coils that, I mean, like the auto transformer. They're whole winding. So when you are in zero position of the knob, there is adjuster knob point here, then that is 0 volt. And then if you want to use 10 volt, then 10 volt. And then connect your circuit between here and here and do some experiment. But this device is called variable AC. This is the other best example of that auto transformer that I was discussing. So therefore, everybody keep in mind this device. It is called the variac. I think electronics lab also does not have variac, but definitely energy conversion lab has that device variac. You remember, it looks like a circular body, and you can control the voltage, whatever you like. Okay, again moving forward. Okay, so this is, so therefore in real life, as I said, the fan regulator, ceiling fan regulator, and then that device you can see. And then also there are lots of application in electronic circuit as well, electronic and control circuit. Frequently this type of auto transformer is used. So therefore with that, for this class at your level, for circuits 2 class, what is the transformer principle, what is the relationship between primary secondary current, what is the turn ratio. I mean, this concept is fine. And then that magnetically coupled circuit. Then once you go to that energy conversion class or other classes, then again we have lots of talk about transformer. There are various tests and other circuit, efficiency calculation, voltage regulation calculation. There are lots of things. So we will discuss those when you'll be going that energy conversion class. Okay, now once again, another problem. Everybody read this. Huh? The primary current to an ideal transformer rated at 3300/110 volt is 5 ampere. Calculate the turn ratio, V, the kVA rating, and the secondary current. You see, in this case, as I said, this is the transformer rating or specification, primary voltage, secondary voltage, and then 5 ampere is the primary current. But this time it does not have that kVA rating. Likewise, the previous 9.6 kVA. This thing is not mentioned here. So that is the question. Question number we find out the kVA rating and secondary current and then turn ratio. Therefore, everybody say once again the turn ratio A. Again, I am doing the same way I did the last time. A V2 over V1, then this over this one. I just kept in that way 1 over 30. And then question B, the kVA rating. What is the kVA rating? V on ion or V2 I2? You remember? Either V on or ion, or we are doing this thing. V on ion is or V2 I2. Yes. So I am doing V on ion because the primary current is given. Still, I did not calculate the secondary current. Of course, with the help of secondary current, you can find out, of course. But first, I am using which thing is given. So I wrote V on ion. What is my V on? This is my V on, 3300 multiplied by 5. And unit is volt ampere. So then I got 16.5 kVA. Then the last question on secondary current. This means what is I2? So therefore you see what I am doing, secondary current I2, V on ion over V2. This means I used V on ion equal to V2 I2. That this thing, I am utilizing this thing. So and then V on ion, that is given again these things, and V2 is 110. So I got 150 ampere. Therefore you see primary current is 5, but secondary current is 150 because primary voltage is higher than the secondary voltage. Accordingly, current is in the inverse. Everybody, do you understand?
Yes.
Yeah. So therefore, again, I already uploaded these things after the class. You all look carefully, and then you will be getting and you will fully understand. Okay, therefore, last problem for today. Now, everybody, you please make a practice. Uh, for the following circuit, determine the coupling coefficient and the energy stored in the coupled inductors at time t equal to 1.5 seconds. We are doing similar problems on the I think on Monday. You see, this is a magnetically coupled circuit. Applied voltage is 40 cosine of 2t, 4 ohm, 1 over 8 farad. This is the mutual inductance, 1 Henry. This one is this side by 2 Henry, 1 Henry, and then dotted point are here. Now, I have written down the answer. Coefficient coupling will be K 0.707 and the stored energy will be 39.1 approximately in joule. You should be getting this result. And then for you, I have written down the energy equation, W half L on ion square L2, then plus minus. So you have to determine what will be the sign of that mutual voltage. That's why I have written plus minus. Everybody, so do you understand what you have to? So at first, everybody, you do. First, convert this into phasor domain. Write down the phasor domain equivalent circuit. That is the fastest. Everybody, please start. Redraw this circuit and convert this one into phasor domain, including the voltage source. This means you write magnitude and angle for this one. Resistance is fine, and you convert capacitor and inductor into the phasor form, impedance form. That is the very first task. Everybody, please do make practice. And then once you are done with that phasor equivalent circuit, and then, because you have to calculate the stored energy, you need I1 and I2. So you assume there is two current. Use two loop equation, I1 current and I2 current. And then you keep going, write down the equation and solve I1 and I2, and then you will be you can use this equation to get the result. And the coefficient of coupling equation was K equal to M over root over L on L2. This is L1, this is L2 as it is, and this is the M value, mutual inductance. So therefore that is K M over root over L on L2. That is the equation. And energy stored equation, this one. You just need to get, you just need to get the value of I1 and I2. Then you are done. L on L2 are directly these values.
Hey, Doc.
Yes.
I noticed the two dots. I'm just making sure I remember this from last class. The two dots are on the same side. Does that mean you're subtracting the mutual? One.
Yeah, right. For example, if you see that, okay, you assume that both current are in clockwise direction. This is ion clockwise, this is ion clockwise. So you are right, it will be subtracting, because if you assume the clockwise current on the first loop, then you see clockwise going for this coil, the dot is not here. That current is leaving the dot. But on the right side coil, if I assume clockwise direction, current is first entering dotted point. So therefore, yes, so you're right, it will be minus sign for the mutual voltage. So therefore, everybody see here, what you I have done. Okay, look this one. I have put dot mark. Julian, now look. Look the equation for mesh on or for loop on. I am writing 40 at time angle of 0 because I converted that source into phasor domain. And look, ion and 4 minus J4 plus J4. I mean, after converting into phasor domain. And then you see minus, here it is J2. So what I am doing, J2 multiplied by I2. See, this current is entering first here, but here there is no dot. So you can say that ion is leaving the dotted terminal. But for I2, I2 is entering the dot. So it is the opposite situation. If, let's say, if this dot would be here, for example, then it would be plus sign because ion was first entering at the dotted point and I2 is entering. So when both current will be entering the dotted terminal, then that is the plus sign. Or they are leaving the dotted terminal. For example, right side, this dot is here, just an example. Then what would happen? I2 would leaving the dotted point, not entering. Here it is entering first. And then of course ion is entering then that would be the plus sign. In this case, it is opposite. Julian, is this fine?
Yeah, I got both equations from KVL.
Yeah. And so did you get both equations?
Yes.
You see, for mesh 2, this is my equation. Like you see, in this side, there is no source, like for first side. So I2, 2 plus J2, and then again mutual J2 multiplied by ion, but minus sign. Did you write this equation?
Yes.
Yeah. Now you solve. Now you have two equations in hand, number one, number two. Everybody please see how I wrote down. So first you see, I constructed this circuit by applying that phasor algebra. This is the phasor domain circuit. From that source, everybody see, this was my circuit, and then I changed into phasor domain. So therefore, everybody look, it will be 40 at an angle of 0. And then you have to convert 1 over j omega c. This on j omega L, j omega L, j omega L. And then I am getting that circuit that I'm doing at the beginning.
So, quick question: why is it negative 4J, not negative J8?
Which one are you talking about? For example, this one?
For the capacitor, why did it go to negative J8? I mean 4, not.
Okay. Because I mean, what is the original formula? 1 over j omega c, right? 1 over j omega c.
Yeah. Yeah.
Okay. And then substitute the value of c. So you are getting 1 over j, and omega is 2. So therefore 8 is going numerator. So you are getting
Yes.
4,
Omega. Yes. Thank you.
you are getting 4 over j, right? So but I want to take the j in the numerator so that I can calculate, because from inductor it is j omega L, all right? J omega L. So therefore it is in the numerator, but here it is 1 over j omega c. I want to make it into numerator j. That's why from denominator I am taking this, then it is changing sign, minus j omega. So is this fine? Yeah. That's why minus j4. Oh, and then everybody notice at the very first I calculated that coefficient of coupling. So which is k m over root over ln L2. So here to apply this equation, even you don't need to change the circuit into phasor domain, because ln L2 are that original values. This is ln, this is L2 as it is, and this is the m. So calculating coefficient coupling is easy. Without changing the circuit into phasor domain, you can use the actual values. So that I did at first, and I got 0.707. And then after that, everybody look, you write down equations correctly for two loops, and then go for solution. So everybody see, then I went ahead, I solved equation 1 and 2. And look, everybody is getting this result or not. Ion should be 7.83 approximately, angle 11.3, and for I2 5.55, angle 56.3 degree. So everybody first make sure that you are getting these two same values or very close. Everybody please make practice. So otherwise on the exam on Wednesday, you cannot complete these things. You must be able to solve whatever way you use. So everybody first write down those two loop equation or mesh equation. Look for this one. And once you get those two equations, then you keep going. Find out ion and I2. Like for example, what I did, I just simplified this one. And then from two second mesh, I wrote down ion equation. I mean, you can do the opposite thing. You can find out I2 and substitute the value of I2 in equation 1. Or from here, you can find something and substitute here. That does not matter. But what I did, from this equation, I found out value ion. And then I substituted ion value into equation 1. And then I got, easily I got, you see, only like few lines. Just I use the pen and paper, and after coming here, I use the calculator. And you make sure that you are getting ion and I2 correctly, these numbers. So therefore, everybody, please your pen and paper, as long as, like, even though by looking you are understanding, unless you make practice by using pen and paper, you might not get that result. So at the exam or homework. That's why I always said that even though you understand the problem fully, but once you go in calculation, that is the issue. So you have to calculate everything correctly and properly. So the calculation is very important for circuit problems, even though you understand the problem well. So you know that last year fall, I mean, everybody listen, last year fall, I was also teaching the same course. And I think there were 28 is similar to you, like you have currently 27 and they have, I think, 28 students. And of course that was, you know, in person physical class because it is last year. And I think not this chapter, in other chapter, Laplace chapter, I gave one problem on the board and I said, you all solve. So everybody understand the problem and they all started solving. And then I wrote down the result that this should be the result. And then I was checking on by one. So 28 students, there are 28 different results. You understand? Yeah. So, I mean, but I noticed that like everybody, for example, started correctly. That Laplace problem, everybody's first few line are the right. And then on the way, different student did differently accordingly. The ultimate result was 28 different results. But then results should be one. So that I wrote on the board. And then the class time was ended. I said, everybody, please try at home. And then next day, several of them were able to get the correct result, but still they are issue. And then I said, I shared my solution. Okay, this is the solution. And when they did very carefully one by one, then they got the result. So that's why, I mean, always I noticed in the circuit class, doing the proper or correct calculation is very important. So that's why you have to be very careful and very minute to solve those problems. Okay, I think the time is over. Some of you have the next classes. So you all keep going. Did anybody get I1, I2 so far?
Yes.
Yes, I got it.
Okay. And then you see in the next page, because there is no time, you see what I am doing in the next page. First, I am converting into time domain from that I1, I2, cosine of 2t. And then you have to calculate the energy at time t equal to 1.5 second. So that I am doing. For t, I put 1.5, and then you see it became 3. And I converted that 3 because this is radian into degree. And then finally I got from here 171.89 and this one. So because there is cosine, so I got I1 minus 7.82 and I got I2 minus 3.7. Both current are minus. And then I calculated that stored energy. Finally, you see, after calculation, and you see, I put the minus sign here because that mutual voltage is minus. So finally, 31.1 joule. This is the result. So therefore, everybody, please you keep going. And I already uploaded this class lecture 25. So you can see on eCoursera, and then you match your result and see. Okay, so do you have any questions, comment, anybody? So I would just say that please make lots of practice and practice.